So to find the z-score, you couldn't use the little baby chart. Of course, you have to do this kind of thing. So how much is going to be on either side? 0.02. You can't look up 0.96 and get anything that means anything, because that would be from there all the way down. It wouldn't relate to the middle 96% at all. So if you look up 0.02, what do you get for the 2.05?
Yeah.
Now notice that the plus and minus is built into the equation, right? That's where this comes from, because you want to go up and down. So all you care about is it's 2.05. Don't freak yourself out and put negative 2.05 in there. Doesn't make any sense. Bless you. So you already knew this from the beginning. Where do you go? 20.79, give or take this many steps. And I can't use this one directly. I have to adjust it because I want a group of 58. So this is my best guess. I'm going to improve on that guess by building a little interval around it and saying I think this interval catches it with this much confidence. So what do you get for the error here? Is everybody cool with that so far? Has everybody got that point? Or hold your peace for a while? What do you get for the error? Anybody do that? 1.106?
107.
107, ooh. I like that. The funniest thing to get all righty about. It's 6. You're crazy. 1.107, yeah. Slap. Plus or minus, do that from 20.79. So I'm going to go up this many and down this many. So you can write your quick little answer in like an interval notation. Oh shit. You get a 19.683 up to 21.897. 097, yeah. No. 897, yeah.
Oh yeah,
Yeah.
I wrote it wrong. I can't read numbers.
That would be a problem, especially in this class. All right, let me, yes. Because this goes to 2. Yeah. All right, guys, let me point out a few things. Would you say this is a very wide interval? No. Why was our error so small? What's one reason why our error was so small? Yeah, the sample was a decent size, right? If I take 58 sample, truly random sample, I'm going to trust that sample pretty well. The larger it gets, the more I'm going to trust it. Also, the original data itself didn't vary very much. Right? Vary, V-A-R-Y, vary, V-E-R-Y. So take a minute, if you haven't done this yet, try to write the conclusion for this. Oh, cool. All right. So how does this sound as a conclusion here? What are you saying? We're 96% confident. Guys, that the interval 19.683 to 21.897 pills contains a true mean number of pills taken by stat students. I like it. So that's what that means. We're 96% confident that that interval catches the real means. There's only a 4% chance that it doesn't. So it's kind of a quick way to tell how confident we were in the first place. You know, how certain we were about what we saw in the first place. If this interval would have been 10 to 30, then I'm like, oh, man, you weren't really sure at all, were you? But this is 19.7 about to 21.9. That's pretty tight there. I'm pretty sure about what we saw. Do you guys get the idea there? This number here doesn't really mean shit. So it's unfortunately misinterpreted, and people are calling for the eradication of this poor little dude because it's misinterpreted. That's never a good reason to throw something out just because not enough people understand it. That's why people take this class. So this just gives me an idea of how certain. The tighter it is to the middle, the more certain we were about that. The further it is away from the middle, the less certain we were about that. So I want to show you, I found a little example. There we go. Which one was it? That one. Okay, cool. Let me zoom in a bit. So this is a study about physical activity and anger or emotional upset as triggers of acute myocardial infarction, which is otherwise known as a type of heart attack. Right? So how much physical activity or your emotional state can either give you a heart attack or maybe you Hulk out, I don't know. So right here, even if we don't understand some of the terminology, you can still see things that look familiar. They got 12,461 cases of acute myocardial infarction. But look here. There's a 99% confidence interval. Because, excuse me, so you are doing something that you've been doing this since day one, but we are really getting to the point where you can find a journal article and you can start to understand a lot more of it than you could have at the beginning. Now you have an idea of how this was created. You know how they created it. And you can see that kind of sprinkled throughout. Eventually we're going to get to the point where we understand what the hell this is. P less than 0.001. That's going to be the next chapter. Alright. So what I like to do is I go to Google and I just type in study and I look over the past week or the past month. And it just comes up with all these studies that have been released. You can get some really, really strange ones.
What's the longest?
Where are we looking? What's the longest humans can live, dude? $122. That's pretty good. I don't know. Yeah, what sucks is that they don't link the original study. Here we go. Oh no! Oh look, dude! Higher than that. Yeah, I got it. Yeah, so cool. Trying to see if they have a confidence interval in here. They have this P stuff again. That's going to become important to us pretty soon. Here you go. Confidence interval right there. You'll have to take my word for it. You can't see it. Confidence interval. And look what they keep using 95% confidence. That's the most used one. Just because. So the only way to be 100% confident, who knows, how can you be 100% confident? You go from negative infinity to infinity, then you can finally be 100% confident. Other than that, you can't. So, So this here is the formula for finding a confidence interval for a mean. When I know this, so we're going to talk about eventually what to do when I don't know this. I've got to take care of that somehow. So let me ask you, just to get us ready for that. If there was a part of this that I was less sure about, should I make my confidence interval bigger or smaller? So remember, if you make it bigger, are you catching more data or not? You're catching more data. So if there is something you're not sure about, should you catch more data or less? So to cover for the fact, so guys, if I want to be more and more confident that I catch the real mean, do I make my confidence interval bigger or smaller? Bigger, because I catch more stuff. If there's something up here that, guys, if there's something up there that I'm not sure about, the way to counteract that is to make my confidence interval bigger. Right? That's going to be taking care of the fact that there's part of it that I'm not sure about. So somehow something's going to change, and I might as well tell you, that's going to change a little bit to cover my ass for if I don't know sigma, if I only have S. S is an approximation of sigma. It's a sample standard deviation. It's not the real standard deviation. So I'm going to have to cover my ass somehow. It makes sense. Got to make that bigger. Cover my ass. This part, again, is the error. What we're about to do is something called feasibility. When I say the word feasibility, does anybody know what that means? I'm not a business person, but it is definitely a business word. Feasible. If something's feasible. Manageable. I like it. So we're about to do something that could be called a feasibility study. If somebody, guys, hey, shut up. If I wanted to be within like 1 year of the real mean age of coyotes, right? If I wanted to be my error to be 1 year off, then I'd have to have a certain size sample to have that happen, right? The larger my sample gets, what happens to my error? It's smaller. It makes sense. The bigger the sample you take, the more sure you are about what you see. The less plus or minus you need to cover for that. Does that make sense? Mathematically, you can see it gets smaller because I'm dividing by that. If it gets bigger, the whole thing gets smaller. But it also makes sense the bigger my sample is, the more sure I am in the first place. I don't need so much coverage of error to cover me for not knowing something. So let me make this equation. Error is this. Is that cool? Because that's what the hell it is. I mean, it makes sense. Can you solve that for n? Do it. Do it. Take a minute. Try to solve for n. There's a reason that algebra is a prerequisite to this course. If you can't solve for n, that's a problem. It does, but it's a number.
It's still a value.
Right? It's a value, exactly. It's a variable now that I've made it. Identify that part as E. Alright. One of the coolest things to realize in algebra is not just the fact that 20 divided by 2 is 10, but that if I have this kind of statement and I change these, it's still true. Of course it is. It's kind of crazy. If I divide 20 by a piece of it, I get the other piece of it. So if I divide 20 by 10, I should get the other piece. So I just turn those. So what does that mean? Put it on. Right, the first step is to shade these. Now if you took longer to get there, I don't care, it's fine. You can multiply by rad n both sides and divide both sides by e and still get there. Right? A little shortcut of that fact. And then to kill the square root u squared. So you get n equals z sigma over e squared, or you can have everything, each one squared individually. So this tells me if I know how close I want to be. I want to be within 5 centimeters of the true distance or something. I can do this formula to see how big of a sample I have to take. If the sample is 18 million, that's not feasible. If the sample is 70, well, we can do that, no problem. We can go look at 70 things, it's fine. You guys, that's why it's called a feasibility. But the question is going to say, how large of a sample would you need? Oh, I don't know what n is. I probably want a formula that solved for n. To be within. Now, a key word for error is within. If I want to be within so much, that is the error. That's how far off I am. So, how large of a sample? Oh, this poor little marker. You're about done. How are you doing, purple one? Oh. To be within 2 centimeters, if sigma is, what you got, Jeff? I don't know, man. 3.09, and we are at 99% confidence. Why do I have to tell you this? Yeah, so I can find Z. So I've got to tell you E. That's E because it says within. That's how far off I think I am. So E is 2. I have to tell you sigma. All right, there's sigma. And I have to give you a way to figure out what Z is. So 99% confidence. That should be on the little baby chart. If you look up 0.99, you get 2.575. Take a minute, make sure you can see that. You can otherwise just do 1% outside, 0.5% on one side, 0.005. If you look at 0.005, it gets you to 2.575. Stop there. Why does it make sense that this z-score is so big compared to the ones we used earlier? Because I want to catch more stuff. I was catching 90, 95%, 96%. This guy's got to go way far out to catch 99% of the data. So the more confident I want to be, it translates into a higher z-score because it tells me I got to go further out to catch that much stuff. Let some of this make physical sense. Now just throw it into the formula to see how big of a sample I need. 2.575 times 3.09 divided by 2. All that squared. Ah, 17 points. What do you guys get? Anybody? No? I'm cool with that. My guess was 17, but I mean, you know, I'm cool with that. That's pretty close.
8274.
Yeah, 15.8. So I get, 15.82, blah, blah, blah. Now, that's how large of a sample. Can I take a sample of 15.82? Little pieces? No. Do you think I round down ever, or do I always round up? Because if it's less than this, then I'm not going to be within as much as I want to be. It's going to be worse. So you always round n up for this. Always. Even if it was 15.12, you make it 16. Because if you went down, your error is going to be worse than you want it to be. So I have to take 16. So is that feasible? Hell yeah. You look at 16 pieces. I like it. Yes, sir.
Does that mean it's not going to be like a normal distribution? It is.
Oh yeah, this one I'd have to kind of know ahead of time is normal, but yeah, we're assuming everything's good to use this. So we'll learn what to do if I don't know sigma. So this is going to have to change a little bit if I don't know sigma, if I only have S. We'll do that next. I think that's plenty for today. Most of you guys probably agree with that. I think the thundering is over.
No.